To begin our understanding, we're just going to work with this simple simulation where we only have two variables, x and y. The way k-means works is you have initial starting points, so those are those x's, and we randomly select observations to be the cluster centers. We then look at, okay, which points are the closest to that cluster center, and then we assign them to be in that cluster. So for example, all the purple points are assigned to that X cluster that falls within the purple region. We then iteratively say, okay, given that that's our cluster center, assign all data points to the cluster that they are closest to. And then once we've done that, we need to adjust where our cluster center is. Because again, we started with something random. We then assigned data points to that cluster center. And then actually the middle of all those data points is going to be different from where it started. Once we've moved our cluster center, that changes which points fall in that cluster. And so we have to repeat this process until eventually nothing changes. So here you see that the red cluster kind of started up further up and to the right, and it moved down to the left. And then eventually the points that fall in that cluster did not change. And that's also eventually the case for all the clusters. And that's how you know that the algorithm has come to a stop and you've determined your clusters. The next thing to understand is distance. So we're just dealing with two variables, so distance is really intuitive, where you could break out a ruler and just measure the distance between the cluster center and the data points. What you'll see in textbook notation are these double absolute value bars, which is the Euclidean norm. So this is perhaps the notation you'll see or something along this, but I like to just kind of write it out long form to better understand it, which is just you take x, y, and z, so as many variables as you have, subtract off the cluster center value for that variable, and then you square those distances. You add up all those squares, and then you take the square root, and that gets you the distance between points. So here, by points, I mean a data point of interest and a given cluster center. The next thing to know is that you need to normalize your variables. So what we have next is the exact same data set, exact same starting initial conditions. The only thing I changed was multiply the y variable by 1,000. So ideally, this wouldn't change anything, but since we're measuring distance, the scale actually matters. And so what you see is instead of clusters doing what you would hope they would do with these obvious kind of 5 different clusters, you end up with these bands because all the importance in calculating the distance is due to the y variable. So it's really important that when you're applying k-means clustering that you make sure that you're standardizing or normalizing your variables such that they all have approximately equal variance. Something else is that what is typically used is the initialization for cluster centers is just a randomly selected data point. So one reason I think this is the case is simply just because it's really fast and simple, just randomly select a data point and that's quick and easy, versus doing some kind of more advanced technique to try to find some good initial clusters. But in addition to that, you might end up in this scenario where if we had random initial cluster centers that weren't determined to be given data points, you might end up with something like this purple cluster where no data points are closest to that cluster. And so when I switch to the animation, you'll see that these 5 clusters become only 4 clusters. So you see that no points are assigned to that cluster, and so as the algorithm moves on, you actually lose one of your clusters. That's not to say I think this can still happen even if you do initialize with random data points, but it's just added complexity in an algorithm that's not really necessary, and I think that's why most clustering algorithms are going to initialize, most k-mean algorithms initialize with just randomly selected data points within the data set. So next, how do you know whether you got good enough results? So we've been looking at one k-means iteration that actually results in the perfect clusters, exactly what I'd hoped for. However, that's not guaranteed to be the case, and what we end up seeing here is the red and purple cluster are kind of splitting what should be just one cluster, and then green and blue, two clusters, are trying to capture three groups of data points. So this is an example of a less than ideal outcome. So the way we ensure that this doesn't happen, or we mitigate the chances of this happening, is to essentially create a target variable of interest. So again, k-means is unsupervised learning, but we're effectively creating a target variable which is trying to minimize the distance between our cluster centers and the data points of interest. And so what you can do is, for any given data point, the error metric is how far away is it from its corresponding cluster center. So you can take that distance, square them, sum them up for all your data points, and that gets you your sum of squares. And that's going to be something we want to minimize. So here I just have 5 clusters with different initial conditions, and you just run out the k-means algorithm, and you'll see in the bottom section the sum of squares. And what we're going to end up doing once they're all done is picking the one that has the smallest sum of squares as our resulting cluster for our 5 cluster run through. And we actually end up with duplicates. Even though they're different initial conditions, they end up with the same final clusters. That's not always going to happen necessarily, but we end up selecting this top right corner. We get the minimal sum of squares of 0.159. And you can also see that relative to the other outcomes that this visually looks like it should be the best as well. So the next step is, we determined how to pick the best k-means for a given number of clusters, but going beyond that, how do we know how many clusters to use? Because we're not always going to only have 2 variables that we can really neatly plot and visually go, obviously we want 5 clusters. And so when we're dealing with more realistic data, we need to do something a bit more generic than actually looking at plots. And so what we can do is take this best k-means for a given number of clusters and then iterate this process for all the different number of clusters we can have. So here I'm taking that 0.159, and that's the result for 5 clusters. I then repeat this analysis for all the different number of clusters, and that's how we end up with this plot. Next, what you'll hear is the term elbow plot, and that's just, we're trying to find the point of diminishing returns, right? And so I threw up an elbow here. So that is, as I add clusters, am I actually getting substantial benefit? Am I minimizing sum of squared errors by adding that complexity? And so this is similar to R squared, where it should always be declining. That's not guaranteed, because you might end up with local minima, not the actual global minima. But assuming you have good results, or you actually have the best outcome for all the given clusters, you would expect this to be monotonic decreasing, and you're just trying to find the point at which added complexity doesn't give you added benefit. So looking at this plot, we know the ideal answer is 5, just because we can visualize the data in this case. I would actually probably say the elbow happens at 4 here. So it gets us close. The right answer is 5, just because I know that because I simulated the data. But based off of an elbow plot in this use case, I would say we should use 4 clusters, maybe 5. Finally, just a drawback of k-means, or not even really a drawback, but just trying to understand how it works, is that you end up with these equally spaced clusters, assuming the variance is kind of consistent. So in this uniform block of data, this is an example of the result you'll see, which that can be useful in some use cases, but where that can become an issue is if you have more complicated relationships in your data. So for example, we have this dual spiral relationship, and there are some clustering algorithms that can capture this and essentially make a cluster that follows that curve of the data. But k-means is just going to create kind of these direct cutoffs, and that's how you end up with this blue on the top and the green on the bottom, which is a less than ideal result for this given data. So just keep in mind, k-means, you're going to end up with these hyperdimensional spheres or blobs, and you can't really capture these more nuanced relationships, although there are some other clustering algorithms out there, such as dbScan, that can capture some of these more complicated clusters. With that, thanks for watching. If you have any questions, please be sure to comment below, and until next time, thanks.